your daily dopamine with Dr. Joe McCullough, where we deliver daily doses of education, entertainment, and inspiration. So sit back, relax, and get ready to be dopamine. Oh, yeah.
It's actually hard because you can't see the screen. And come say hi. All right. Hey, welcome to Ask a Physicist Anything with Paul Graham.
And Joe McCullough.
Today we're talking about the twin paradox. So let me just quickly set up the twin paradox for you and then let Paul take over. So one of the things we went through is anytime you're traveling at speeds near the speed of light, or actually any speed, time actually moves forward at a slower rate for a person traveling at speeds near the speed of light, or any speed for that matter. So let's say you have two twins, Bob and Mary, and they are exactly the same age biologically. Bob decides to stay on the Earth while Mary gets on a spaceship traveling at, let's say, 80-90% the speed of light. According to Bob, he sees Mary moving at some huge speed. He says time for Mary is slowing down. However, according to Mary, she would say, no, I'm at rest, and Bob, you're moving the other direction at 80-90% the speed of light. Mary's going to say Bob's time is slowing down. Now, what happens if Mary then returns back to the Earth? Who is going to be right? Obviously, one of the twins is going to have aged differently. So Paul is going to talk about the twin paradox.
All right. Yeah, that was a great intro by Joe. You know, one thing that I always like to emphasize when we talk about the twin paradox, we don't call it a paradox because it's weird or it's unexpected or it's not the way we're used to time behaving. This is what would happen in relativity. If you could build a spaceship that goes 80% the speed of light, then yeah, every 3 minutes that pass on board the spaceship, 5 minutes will pass for the observers at rest on Earth.
Somebody says purple looks good on you.
Oh, thank you.
Thank you, Lily.
If Bob says the entire trip is going to take 50 years, 25 years out, 25 years back, but Mary's going at, again, 80% the speed of light, she plans for the whole trip to take 3/5 of that. It's going to be 30 years. Where did I get that exact number? You remember we gave you the equation last time, for those of you who are the math junkies. The time that passes for Mary should be shorter than the time that passes for Bob by this little blob of math right here that appears all the time in special relativity. That's where I'm getting the 3/5. If I make V over C be 0.8, you do out the math, you get exactly 60%. So Mary's time is going to be 60% as long as Bob's.
So Lily, at some point, somebody wants to know the difference between molecules and ions. We'll throw that in the queue.
Awesome. We were just talking about that last night in my class. So far, you know, you'd say, hey, I didn't expect time to work this way, but then I've never done much traveling at almost the speed of light, so maybe it does. And in fact, it does. We can have subatomic particles go at 80% the speed of light and much faster than that, and this is exactly the way time works for them. Now, the paradox isn't that, oh man, that's weird. That's something I'd have to wrap my mind around. You know, my twin sister could be 20 years younger than me. That's weird. Well, no, it might be weird, but it's not paradoxical. The paradox is just what Joe said at the beginning. Take this from Mary's point of view. She has every right, once her spaceship hits cruising speed, to turn off the engines, coast, and say, hey, I'm at rest now. It's Earth that's receding from me at 0.8 C that way. So she'll say, okay, time's passing normally for me. Time should be passing slower for my brother Bob. Then for the second half of the trip, after she turns around on her way home, and again she's hit cruising speed, again she can say for that whole half of the trip, I'm just sitting here at rest. Earth is coming back toward me. Okay, that means time's passing normally for me, time is passing slower for Bob. In fact, if she runs this same formula here, she'll say, okay, Bob should experience 60% as much time as I do. So if I age 30 years during this trip, I guess Bob will only age 18 years. Well, she lands back on Earth, steps out of the spaceship, expecting to see her brother sprightly 12 years younger than she is, and instead there's this guy 20 years older than her. And she says, who are you? What have you done with my real brother? Well, okay, the Laurel and Hardy routine is not the paradox. The fact that they both seem to have reasoned correctly, yet the answers they get can't both be right, that's the paradox.
So somebody has to have aged at a different rate, and they can't both be right in this case.
Yes, it's fine if it turns out that one clock, that time passes at a different rate for one observer than the other. Hey, we weren't used to that before we discovered relativity, but that's just what happens. But if you say, no, we're both making the same prediction. We're saying when Mary and Bob step out, shake hands at the end of this journey, is Bob going to be older than Mary or younger than Mary at that moment? You can't have that one both ways. That's not something it just depends on the reference frame. So, there we're saying if there's going to be a consistent reality here, you got to get one answer or the other.
So, hey man, the answer will always be the same. Paul's going to go through who we can trust, why. But yes, in terms of one person staying on the Earth, another person going on a spaceship, the end result will always be the same, given this setup.
Oh yeah. To give you spoilers,
trust no one.
When we run this experiment, Bob's going to spend 50 years hanging around on Earth. Hopefully he brought some other stuff to do. Mary's going to spend 30 years on the spaceship. When she gets home and steps out of the spaceship, in fact, it will turn out to be Mary who is younger, Bob who is older. Less time will have passed on the ship. But Mary still has every right to an explanation saying, wait a minute, I spent the vast majority of this trip just hanging out at rest. My brother was moving. Why is it him who would be older? I thought he should be younger. Okay, the answer to that is special relativity, the idea that there is a principle of relativity, that an observer who's moving along at a constant rate has the right to say, I'm not moving, it's the rest of the world that's moving around me. That goes back to Galileo, actually, and that was a radical thing back in Galileo's day. As Mary's using it now, she's saying, all right, we've updated the way the principle works. Special relativity is different from Galilean relativity. But even back in Galileo's relativity, there was one caveat to that. You had to say, okay, if you want to say I'm at rest and everybody else is moving, that is fine as long as the vehicle you're in is not accelerating. If it's moving at a constant speed and a constant direction, then you can draw coordinates on the side of that vehicle and say, from now on, this is what I consider to be at rest. And physics will work perfectly as measured from on board that vehicle. But if the vehicle's accelerating, if I'm in a bus that's traveling down the freeway at a constant speed, I can close my eyes, not look out of the bus, say, we're at rest. And if you tell me that you see cornfields moving by outside, fine, the cornfields are in motion. However, the moment my bus speeds up or slows down or hangs a left turn or something like that, suddenly I feel like there's this mysterious force out of nowhere pushing me, forward in the bus if the driver slammed on the brakes. At that point, even Galileo would say, okay, now you got to admit that your bus is accelerating. It's okay if you want to say it's not moving when it's moving at a steady rate, but if its velocity changes, that's something you got to take into account.
So even Newton's laws don't apply in all reference frames. For those of you into physics, Newton's laws only apply in an inertial reference frame, which is one moving at a constant velocity.
You can use Newton's laws in that accelerated frame, but the price of admission is you have to treat fictional forces as if they were real. So if you want to act as if that mysterious force pushing you toward the front of the bus had actually happened, if you want to include that in your Newton's law calculations, then actually the accelerated frame works fine. But Mary's is inheriting that same point where you have to be careful from Galilean relativity. It applies in special relativity also. She does have every right to say, my spaceship's at rest. Bob's planet is the thing that's moving, as long as her spaceship's moving at constant velocity. Now, for most of the trip, it is. At the beginning, she might have had to speed up to get up to 0.8c, but we could even say, no, let's just say she's already in motion before we start the experiment. She high-fives Bob out the window as she goes by, but she's already coasting by at 0.8c. Don't try this at home. High-fives at 0.8c are tricky. These are trained professional stick figures. As she reaches the end of her trip, whatever her destination planet is over here, 20 light years away, if she's going to go back and have that rendezvous with Bob where they can actually compare ages, she needs to turn around, which means she does need to change her velocity. She needs to accelerate that way. So she's moving along. She has every right to say, I'm at rest, Bob's moving. But as soon as she starts to accelerate, you'd say, okay, now you are switching from one reference frame to another. In fact, as she was on her way out, you could say that her reference frame was coasting along at constant velocity this way. While she's on the way in, she's switched over to a frame that's coasting along at constant velocity this way. And that switch of reference frames is what is going to complicate her calculations. There are ways she can adjust for that. It's not that she has to just throw up her arms and say, I don't know what's going to happen. I'll find out when we get there. Speaking of the characters in Interstellar.
Stop hating on Interstellar.
But if she doesn't make those corrections, then yeah, she is going to get the wrong amount of time. So we said it seemed to be a paradox because she was correctly predicting that Bob was going to be 12 years younger than her when she got back. No, that wasn't a correct prediction. She forgot to take into account the acceleration of the spaceship. Now, if she does take that into account, then everything's good. There's an issue in relativity called simultaneity shifts. We've told you a few things that are strange and unexpected that go on in the way space-time works in special relativity. One of them is time dilation. If you are in a vehicle that is moving fast compared to the observers at rest, they will measure that less time passes for you on board your vehicle than the amount of time that passes for them. There's length contraction. If you were to ask a related question on this, hey, I said that planet was 20 light years away. And if you said 20, you said 25. Well, no, we said it takes her 25 years to get there in Bob's frame. Remember,
real quickly, I have a question, but even if she never goes back, isn't Bob younger? So let's touch on that at some point.
Well,
what happens
yes.
if she doesn't turn around?
If she doesn't turn around, then the two of them actually will continue to disagree. They will each measure that in their frame the other person is younger because of these simultaneity issues. So we got time dilation, we've got length contraction. Let me tell you just very quickly. If that planet's 20 light years away and Bob says, hey, it took Mary 25 years to get there because she's moving a little slower than the speed of light. That's cool. But hey, Mary says she took 15 years to get there. Now, she might say the planet came to her, but if this was really a 20 light year distance, and this planet covered that distance in 15 years by her calculations, man, the planet's going faster than the speed of light. I thought that wasn't supposed to happen. Well, in fact, it doesn't happen. If Mary measures the distance between the planets while the planets are in motion relative to her, she's going to actually measure that that distance is contracted. She will not say it's 20 light years of distance. She'll say it's 12 light years of distance.
And let's just be clear, it's not just that she's measuring a smaller distance.
It's not that she's making a mistake in the measurement. She's doing the measurement correctly. The amount of space between those 2 points depends on your reference frame. The faster you are moving through space-time, I keep coming back to saying the smaller you'll measure that distance to be, but we're not saying it's a mistake in the measurement. The smaller that distance is.
So if you saw a planet flying by you at point 8c, you wouldn't see the planet as a circle. You'd actually see it as some kind of oval because
Yes.
one dimension would be contracted, the other dimension wouldn't.
Yeah, or at least you'd measure it to be an oval. If you say, what would you see, then you got to take into account, but man, how long did the photon from that end of it take to hit my eyes? And how long it gets weird when the signals that reach you are moving at speeds comparable to the thing you're trying to measure with them. But the simultaneity is a fact that relativistically 2 events, if I just ask, did these 2 events happen at the same time? Never mind how much time passed between them. In fact, if they happen at the same time, I'm trying to say 0 time passed between them. But if I say, all right, I'm going to snap both of my fingers, did I snap those fingers simultaneously? Well, relativistically, the answer to that actually, again, depends on your reference frame.
Quick question, would traveling through a wormhole cause a similar time dilation? Just we'll throw that out.
Okay, yeah. Well, wormholes in general relativity, we actually will kind of loop back around to that. But it turns out that the example I always like to use of this is what they call the barn door paradox, or I'll call it the spaceship hangar paradox. Suppose Mary, once she returns from this long trip, decides to celebrate with her friends that night. They all have a little bit too much to drink, and Mary ends up making some unwise wagers over the course of the evening. Wakes up the next morning with a crumpled up napkin lying next to her.
Corey.
Says, what's it say on here? It says, I just bet a large amount of money and even more pride that that my spaceship fits in that hangar across the street. And by the cold light of morning, she looks over at that spaceship hangar. Here's the size of the hangar. Here's the size of the spaceship.
So let's just make the spaceship twice as big for...
Okay. It's not going to fit. The spaceship's parked right next to the hangar. No way in hell she can fit the spaceship in there. However, being an interstellar pilot, she is not going to be defeated that easily. She says, wait a minute, this ship goes at a good fraction of the speed of light. I'm going to get this ship up to near light speeds, and the ship will be length contracted. So I can buzz it through the hangar. There will be this moment when I hire my flunkies to slam both doors of the hangar simultaneously, take a picture, and prove that for my fast-moving spaceship, which is length contracted, moving at, almost the speed of light here, that, yeah, it did fit inside the hangar. So, she says, okay, my reputation is rescued. I'm not going to lose this bet after all. Gets in the ship. Probably burns more fuel than the bet was worth in the first place, but this is pride, damn it. And as she's zooming toward the hangar, she starts to reconsider things, and she says, wait a minute.
The answer is yes.
From my point of view now, my ship's at rest. It's still its normal length. But you know what's length contracted? The hangar's length contracted. It's moving toward me at almost the speed of light. So she's going to say, all right, suddenly this does not look like such a good idea. Because what I am now seeing is...
Is length contracted to the observers of the ground or the passengers? That's what we're kind of talking about right
Yes,
now. It depends upon your frame of reference.
Yeah, any object which is moving with respect to you when you measure it, you will measure it to be length contracted. When I said Mary measured the distance between those planets to be length contracted on my first example, it was because those planets are moving along at a constant rate with respect to her spaceship. In this case, the people on the ground say, hey, Mary, great plan. This is going to work. We can slam those doors because your spaceship is length contracted. It's moving real fast relative to us. However, on board the ship, Mary's having second thoughts.
Poor Mary.
She says, my ship, it's at rest with respect to me. It's its normal length. This spaceship, or the hangar, which is now racing toward me at almost the speed of light, it is going to be strongly length contracted.
So in this case, the passenger being Mary, she's going to measure her own spaceship to be its normal rest length.
Right.
She's going to see
by her
the garage or whatever this is, hangar moving towards her. So in her frame of reference, it's the hangar that's contracted.
And
oh, wow, finally got it. Woohoo! Hey, man!
And so she looks at this, she says, oh man, it's too late to back out now, but I don't think this is going to work. And damned if it does. She, the hangar starts to pass by her ship. Both doors do slam, but both doors miss her ship. And she said, man, that happened so fast, it was kind of hard to tell why. Because the thing was moving at 0.99c. Of course it happened fast. But if she kind of goes back, analyzes the records later, she'll say, all right, my flunkies, my graduate students on the ground, they did slam both those doors. I don't think they slammed them simultaneously. Because she's going to say, here's what happened. Door B slammed first. And in fact, if these people want to avoid having to pay the deposit on this hangar that they rented, they could have plans to slam the door and then reopen it immediately. If they don't, then they just have to add that to the fuel bill we already talked about because they're going to demolish door B. But either way, door B slammed. Door A was still open by Mary's measurement at that moment. And then door B either reopened or smashed over the nose of the spaceship, whichever one they do. The hangar continued to move past the spaceship. And then later on, once door A was already clear of the back of the ship, that was when door A slammed. And she says, I think they might make me forfeit this bet. Those doors didn't slam simultaneously. But she looks at the records kept by the people on the ground, and by their measurements, those doors did slam simultaneously with the spaceship safely inside. In other words, both of these events happened. Door B slammed. Door A slammed. They both missed the spaceship, at least at first. The thing that nobody seems to agree on here, or the two frames don't agree on, is did those events happen simultaneously, or did they happen at different times? And it turns out in special relativity, that is yet another of the things where the right answer actually depends on the frame. Now, if you say, how can cause and effect even survive? Cause and effect survives because no information can travel faster than light. So if you slam door B, and then the person who slammed B says, you know what, Mary doesn't pay us enough for this. I'm going to tell the person at door A just not to slam that door at all. And as he slams door B, he sends that message to the person at door A. The message will not get there in time to affect what happens at door A. So even though the order that these events occur in depends on which observer you're asking, The question of can you get a message from event B to event A is no in every reference frame. Doesn't matter how fast you're moving, in what direction, if those events are simultaneous in any frame, then no matter what frame you're in, they're far enough apart that there's no way to break cause and effect. There's no way to get a message from one to the other, assuming that messages can't travel faster than the speed of light. That's one reason why those faster-than-light neutrinos that they thought they found a few years ago were causing quite a stir of excitement in the physics community. We knew they weren't really faster-than-light neutrinos, but it was fun to dream.
Are you getting into quantum entanglement there? No, we are not.
No, that is a separate thing. Although we can loop back to quantum entanglement next week. let me finish telling you how simultaneity relates to that twin paradox, though, because you asked, hey, what if Mary does not turn around? She just keeps going forever. Who's younger, her or Bob? Actually, it turns out that can be something that does depend on who you ask. If they meet again and shake hands, they're face to face, they have to admit, they at this moment, one of them is older than the other. However, if they are still in very different places, the order that events happen can be different for the two people. In particular, Bob would say, here's a timeline of what's been going on. At year 0, Mary launches her spaceship. And he's going to say at year 25, Mary reaches that planet where she was planning to turn around. And maybe she decides, I'm not going to turn around. I'm just going to keep going. Okay, that's fine. But you could still ask him, hey, how old is Mary at that particular year? He's going to say, well, she has aged 15 years since the experiment started. Now, if you ask Mary what's going on, she's going to say, all right, here I am on my spaceship. What's my timeline? Year 0, she says, I launched. Year 15, I reached the planet. And again, I'll just decide to keep going. And she would actually maybe say the planet coasts by me rather than saying she reached the planet. However, and she says, okay, this is simultaneous with, well, Bob is going to say, look, see, I told you you were the one who's moving. My celebration on year 25 years without my sister, yay, is simultaneous with your celebration of year 15 of your voyage. And she's going to say, no, I agree, both those events happened. You threw that party. It was in bad taste, man. I didn't celebrate you being gone, but you threw that party. That's fine. It wasn't simultaneous with this 15-year mark, though. She's going to say, no, that was actually simultaneous with your 9-year mark. So Bob says, hey, nothing special happened at 9 years. And she says, yes, it did. At that same moment you were celebrating year 9, I was reaching that planet. So it's kind of like the barn door paradox here. They both agree that all 3 of these events happened. They agree Bob threw a party on year 25. Bob threw a party on year 9. The ship launched on year 0. Bob says, okay, I agree the ship launched on year 0. And Mary, passed that planet on year 15. They disagree on which pairs of events are simultaneous. And if you're saying, could we use this to break the structure of cause and effect? If Bob's saying, all right, Mary won't reach the planet until year 25, what if on year 9 at that party he has a tearful change of heart and says, I don't want her to be gone that long. I'm going to send a message, tell my sister to come on back for a reunion. That message will not reach her until well after that year 15 passage of the planet. So you cannot change the order of what events can cause which other events, but you can change your understanding of what order the events actually happened in and which were simultaneous to it.
Let's pause for 1 second. Hey man, did you have a comment that I missed or a question that I missed? If so, type it in again and we'll see if we can get to it.
All right.
So you want to do a quick little, hang on. Okay, we'll hang on for a second. You want to say another minute while he's doing something?
Okay, sure. If she does turn around after all, so if she keeps on flying forever, they are both moving at different velocities. Each one would say my velocity is 0, the other person's velocity is away from me. They will keep on getting farther and farther apart, but they will continue to disagree until the end of time about who is younger and what order these events are happening in.
The question is, if Bob travels to Mary, will he catch up in age?
If he travels to Mary, then if we had a third person, Ernie, also standing on Earth, Ernie's going to say, okay, Mary is experiencing some time dilation because she's moving pretty fast. 3 years are passing for her for each 5 years that pass on Earth. But then he's going to say, if Bob tries to catch up to Mary, man, he's going to experience even stronger time dilation. And in fact, let's see, if he does catch up to her, it will be, which one will it be? It will be Bob who is younger at that point.
Because he's going to have to be traveling significantly faster than 0.8c.
Yes, and you could also say that from Mary's point of view, now it's Bob who accelerated. She can say, hey, Bob, you spent the first half of this story receding from me at a steady rate in that direction. Then you accelerated. You changed your velocity. You got on that spaceship and boosted up to really high speed. You spent the second half of the trip closing that gap with me. And since she never accelerated, she coasted the whole time. Now she's in the position of she can now be the observer who was at rest the entire time. Bob's the one who was first receding from her that way, and then after that really fast spaceship boost was coming back and closing the gap with her. So now she's actually going to say, yeah, Bob is going to be the traveling twin of the twin paradox. Bob will be younger by the time he catches up with me. Ernie would agree, but he would agree for a different reason. He would say, hey, Bob was started out at rest. Mary was not at rest the whole time. But since Bob had to be actually outrunning Mary, going even faster than her, his time dilation on that second leg of the trip was even stronger. And yeah, by the time he catches up with her, so little time has passed for him during that part of the story that he's going to be the younger twin. So they on things that are actual aspects of reality. When Bob and Mary shake hands again on board this spaceship after Bob catches up, who will be younger? That is something, now they're in the same place, so you can't have any simultaneity shifts. They're standing face to face. You can't disagree on which one reports that they've experienced more time during this, or if they've both brought their measurement devices, you can't disagree on which clock reads more time. So at this point, all observers will have to agree, yeah, Bob is younger than Mary by such and such number of years. They will disagree on the reasons why they made those calculations in that order, but they will all agree on the results. As long as the people are distant from each other, simultaneity becomes another thing that they can disagree on. So when they were still distant and receding from each other, Mary really could say, hey, yeah, this is the 15 mark for me. Back at home, Bob has only celebrated 9 years since I left. Bob, meanwhile, can be saying, hey, I agree that's the 15-year mark for you over at this event, but it's simultaneous with this event. I was celebrating 25 years. Again, they both agree all these events happened. And if he's throwing yearly parties, they both agree the T equals 1, 2, 3, 4, 5, all those events happen, but they disagree on which two events were simultaneous with each other.
All right, so I think that's good for twin paradox. We have about 5 minutes. You want to just quick 5 minutes? Question we had was, what's the difference between a molecule and an ion?
Okay.
Going back to some non-relativistic physics.
Okay, start with an atom. An atom is a small lump of protons and neutrons in the nucleus, surrounded by a cloud of electrons. Notice I say cloud, not individual orbiting electrons on trajectories like we draw it in corporate logos or something, because in quantum mechanics, objects do not have specific well-defined trajectories. Even if this is a hydrogen atom with only one electron, that electron is still a probability cloud around the nucleus. But there's a single atom. Let's say this is a carbon atom.
Will electrons orbit the nucleus of atoms for an infinite time? The answer is no. Electrons, they'll get knocked off. It's not like it's going to be stayed there.
You can do something to knock them out of the atom, but if you leave the atom alone,
yes,
the electrons should stay there forever. In particular, if what you're asking is, do they gradually lose energy as they orbit? No, they do not. And this confused people. There were many reasons to think they should gradually lose energy. In fact, that atoms should not exist for more than a tiny fraction of a second before the electrons fall into the nucleus. Quantum mechanics came to the rescue and explained why they do not lose energy once they've reached their ground state.
This is the exact question somebody had.
Oh, okay, cool, awesome. So if this carbon is forming bonds, I'm going to make a methane molecule. Methane molecules would be like a tetrahedron in 3 dimensions, but I'll draw it flat on the board. These would be hydrogen atoms, and as their electron probability clouds overlap with the carbon, this is how you form those bonds between the atoms. So now the hydrogens can be in a lower energy state if they remain attached to the carbon. So this would be a methane molecule, except that I've drawn it flat instead of the proper three-dimensional tetrahedron structure.
So a simple definition of a molecule is?
Several atoms connected together by chemical bonds.
Excellent.
What an ion is so far the total charge of this thing is 0. The nuclei all have positive charges, but the electrons have negative charges, and there are just as many electrons as there are protons. The carbon came in with 6 protons. It had 6 electrons in this cloud. Each hydrogen came in with 1 proton, and it had 1 electron in its cloud. Altogether now, I've got 10 protons on the board. I've also got 10 electrons. If I were to knock off one of those electrons, Joe was saying, hey, well, you can come by with a particle with a lot of energy, and it could just knock one of those electrons out of the atom. Well, that can happen to an individual atom, or it can happen to this molecule. So boom, there went a fast-moving cosmic ray particle that just knocked one of those electrons out. This methane molecule now has a positive charge, and that is an important enough distinction in chemistry that they give that the name ion. Any atom or molecule that has a non-zero charge, if it has a positive charge because it's lost an electron, or if it has a negative charge because it has gained an electron, if, for example, when you dissolve salt in water, that sodium chloride crystal breaks up, and the sodium ions and the chlorine ions separate from each other and go their separate ways, floating around among the water molecules. However, the chlorine ions take with them a souvenir. They get to keep one of the electrons from the sodium atom, and the sodium atom has lost one of its electrons. Now the sodium is a positive ion, it's Na+. The chlorine is a negative ion, it's Cl-. In this case, my methane, my NH4, has a positive charge. So this is now a methane ion instead of just a methane molecule. That's the only difference. If it's neutral, we call it an atom if there's one of them, or we call it a molecule if there's several atoms bonded together. If you have added or removed the total electron, so if the total charge is not 0, then you call it an ion.
Lily says, been trying to study all day and you guys explain it in 2 seconds. That's because Paul is a master. Okay, Bobber, we are just about done. So, today, episode 5, Ask a Physicist, we were talking about the twin paradox and then touched a little bit on difference between molecules and ions. Thank you so much. You are so welcome. So, Paul.
All right, we'll see you next week. We could follow up on quantum entanglement since people were asking about that again, or anything else.
Yeah, and if people have questions, I think the easiest way to get them, go to my YouTube channel, just search for Joe McCullough. I have a playlist, Ask a Physicist Anything. Leave a comment on one of those videos, and then I'll get through that. If not, then we will be here again Wednesdays at 3 o'clock. And, oh, you're going to put your email.
I'll put my email. They can get me through there.
Oh, Paul's giving out his email. Paul
the reason
Graham.
Joe says, ooh, is I'm a notoriously lousy email correspondent, so this will encourage me to remember to check my email.
So Paul Graham, Pagraham @cabrillo.edu. All right, well, Paul, thank you so much. Enlightening as always.
All right,
My name is Joe. Thank you so much. Hope to catch you guys next week. And if you like physics, every Wednesday, Ask a Physicist Anything. All right, Paul, thank you very much. I always love watching your scopes. Lily, thank you so much. I do catch all of these, so you can watch the replay on Catch, and I do upload all of them to YouTube. All right, have a wonderful Wednesday, and thanks for watching.